Good afternoon and welcome to Advanced NMR Spectroscopy course. So today now I'll continue with the application of NMR spectroscopy specifically for organic molecules. Okay, so I'll first do a little bit of revision and then we'll go into the problems. Okay, so first I will discuss about the symmetry and spin system, because this is very essential to understand to analyze the spectra. Although I have told in my earlier classes about symmetry and spin system, but still I will tell some of them and also give additional examples. So if you remember that I discussed about the effect of symmetry on NMR spectra. So when a nuclei in a given structure will be distinguishable in NMR spectrum and when they will not be distinguishable. Okay, so that thing I told you, again I will repeat that. So the test of distinguishability is based on the symmetry relations among the nuclei. So symmetry is very important. Okay, so there are three types of symmetry elements. All of you know it: axis of symmetry, planes of symmetry, and centers of symmetry. I will not go into the details of the how you define all these things, but all of you know. So that about the center of symmetry, and then axis of symmetry, and then plane of symmetry. You can see the examples also, the CH3Cl and CH2Cl2. In the former case, you have a C3 axis, other case you have a sigma V, and then you will see the center of symmetry. Okay, so you can see that here each pair of atoms, okay, so what you will see in the center of symmetry is that you will have a companion atom located at the same distance from the center along a line through the center connecting the atom. Okay, so you can see clearly this hydrogen and this hydrogen. Okay, that is the center of symmetry. Similarly, this hydrogen and this hydrogen. Okay, so symmetry equivalent nuclei are chemically equivalent. Okay, and they will be indistinguishable by NMR. So they will have the same resonance frequency, so isochronous, and they will have the same chemical shift. Now, based on the symmetry elements present in the molecule, all the molecules can be classified either they are homotopic, enantiotopic, or diastereotopic. So nuclei, those that are equivalent by virtue of CN axis. Of course, N has to be greater than 1 because C1 on all molecules possesses C1 axis. So it has to be more than 1, said to be homotopic, and they are isochronous. So automatically they will give one NMR signal like methylene chloride, methyl chloride, and so on, and methylene chloride. Now, if you see that if two nuclei is equivalent by virtue of a sigma plane, okay, but there is no CN axis, okay, then they are called enantiotropic. Okay, and the enantiotropic nuclei also will also give you one signal. Okay, you can see this chlorobromomethane. Okay, okay, so you can see that those two hydrogens are not they are enantiotropic. Okay, and how you will check the whether they are enantiotropic or not? You replace one of them, you will get one enantiomer. If you replace the other hydrogen, let us say even with deuterium, you will get the other enantiomer. So that's why they are called the enantiotropic. Okay, you can see the this example. These two methyl groups are enantiomer, because if you do any reaction on this methyl, it will produce one enantiomer. If you do it other, it will give you the other enantiomer. Similarly, these two hydrogens are also enantiotropic. Replace one of them with some other group, you will see one enantiomer, and that will give you other enantiomer. But if you look at this molecule, okay, this molecule, see there is a chiral center. All the four substituents are different. So now these two hydrogens, okay, see you can see there is no symmetry element here. So this is an asymmetric molecule. Okay, and you see these two hydrogens are no more equivalent. So that's why they are called the diastereotropic hydrogens. Okay. So that's why the two hydrogens, if they are adjacent to a chiral center or even a little bit far away from the chiral center, are called diastereotropic. Okay, and they are not chemically equivalent, and you can expect them that they will resonate at different frequency. But you know, sometimes these are called the accidental chemical equivalents. Okay, so that is not due to this. That is happening because somehow the resonance frequencies are same. But if you change the NMR machine, let us say you go from a low field to very high field machine, you will see that they will be coming at different position. But whereas in case of when they are they have the same chemical shift, irrespective of the machine, they will come at the same place. Like enantiotropic hydrogen, they will come always at the same place, irrespective whether it is 60 megahertz, 100 megahertz, 200, 500, 600, it does not matter. Okay, so that's what I am telling you about the accidental equivalence. So nuclei that are not symmetry equivalent, okay, but precesses at the same frequency. Okay, so there is no symmetry, but still they come at the same frequency in a particular magnetic field, are called accidental equivalents. Okay, so if you change the field strength, they may not appear at the same position, or they will rather appear at a different position. For example, this cyclopentanone or even this acetylene, you see this is this methyl and this hydrogen, accidentally they come in the same position in a 60 megahertz machine. Okay, now let us see how conformation okay, so how conformation affect the symmetry. Okay, now if you see the toluene, that this example I explained, you see toluene having you have a aromatic ring system which is planar, whereas the CH3 group is not planar. So if you consider even there are two possible, let us say, rotamers, the rotational isomers or conformers, which are obtained by rotating this carbon-carbon single bond. You can see this is one conformation where these two hydrogens, okay, and you can see the three hydrogens are not equivalent here. Okay, so in this situation, you will see that the two ortho hydrogens are equivalent. You will see two meta hydrogens are equivalent and para hydrogen, and you will see that these two hydrogens are equivalent, whereas this third hydrogen is not. So what you will see, if you fix the conformation in this particular state, you will see that you will get 5 proton NMR signals due to 5 groups of protons. Similarly, you will see 5 carbon-13 signals also. Now let us take another conformer, okay, where this HB is in the same plane of the aromatic ring. And then you will see that again you will have, now you will see that your this hydrogen and this two ortho hydrogens are no more equivalent. Similarly, these two meta hydrogens are also not equivalent. Okay, and similarly, see this HA hydrogens, which in this case we saw, are also not equivalent. So you will see total 7 proton signals and 7 carbon-13 signals. Okay, but in practice, we see that toluene, we see only the 2 ortho hydrogens are coming at the same place, 2 meta hydrogens coming in the same place, 1 para hydrogen, and you will see all these 3 protons, they come at the same place. Okay. Okay, so they become chemically equivalent because of the free rotation. We will see that the situation, we will call that the rotation of this carbon-carbon single is very fast compared to the NMR time scale. We'll discuss that, the NMR time scale, maybe after 2-3 lectures, we'll come to that. We'll see the dynamic NMR. At that time, I will explain what is NMR time scale. And we will see that depending on the NMR time scale, we will see the there is a change in the इसको एंटर करो ना ये दो हाँ okay. So if the rotation is fast, the methyl protons averaged out and they become chemically equivalent. Okay. So as if this methyl group behaves as it has got a C3 axis, rendering all three hydrogens equivalent. And we will see that we will utilize this concept in analyzing bigger molecules. Okay, so what we will see in bigger molecules, that we will not see the whole molecule, the symmetry of the whole molecule. Rather, we will see the symmetry of the individual group of protons. Okay, we will see that with one example later on. Okay, so that way I told you, if it is a slow in NMR time scale, you will see there is the methyl protons are not coming at the same position. Okay. Now let us see. This is a simple molecule with molecular formula of C5H6O, and they are all cyclobutanone derivative. Okay. Now, if you see that, can you tell which compound will have the simplest NMR? So you have to see the symmetry of these molecules. Now, here also you can assume that CH3 protons, all the three hydrogens are equivalent. Okay. So if you see that, so the molecule A will have one symmetry element, that is the sigma plane, which is the molecular plane of the molecule. Okay, and you will see that, because then you will see that these two hydrogens become equivalent. So you will get a three NMR signal, one due to this hydrogen, one due to these two hydrogens, and one due to the methyl. So very same thing is molecule B. Here is also a sigma plane, but these two molecules are slightly different because the chemical shift of hydrogens will be different. Okay, because this hydrogen is here, it is beta to the carbonyl, whereas it was alpha to the carbonyl. Okay, so here again you will get the three sets of signals. Okay, now see the molecule C. Now you see there is no symmetry element present. Okay, except the C1. So we do not consider the C1 symmetry. Okay, so you will see that all these protons, this methyl group, this hydrogen, this hydrogen, this hydrogen will come in separate different positions. Okay. Now, if you see these are same molecular formula, now you see this is a very, this molecule is having much more symmetry. So there is one C2 axis. You can see this is the C2 axis passing through this carbon, this carbon, this carbon, and oxygen. And there are two symmetry planes, two sigma planes. This is one plane which is bisecting the molecules, another is the molecular plane. So that's why you will see that you will get only two sets of signal for the molecule D. So that's why if the molecules become more symmetric, you will see the number of signals are also getting reduced. Okay. Now another term. So far I discussed about the chemical equivalence, but there is also another term called magnetic equivalence. I discussed this thing in my earlier classes also, but still I would like to use it because I will be now using these notations very frequently during your coming all classes. So let us see what is magnetic equivalence. Now what we have seen that protons couples with each other and resonance signal splits. So when they couple each other, when they are not equivalent. Okay. So when they are not equivalent, they can couple to each other, and that brings you splitting in the signals. Okay. Now the nuclei become chemically equivalent. When they become chemically equivalent, if you have there is an axis of symmetry or center of symmetry or a plane of symmetry. I have explained you with in my previous slides. Now we have also seen that chemically equivalent protons. Okay, if you see the chemically equivalent protons precess at the same frequency, that means they are isochronous. Okay, and chemically equivalent protons do not have spin-spin coupling. Okay, but this is not totally true. Actually, they couple each other, but we are not able to observe that coupling. Okay, we'll see that how to find out when the chemically equivalent, how to find out the coupling constant when the protons are chemically equivalent. That also I will tell you, and I have already told you if you remember, but still I will tell you today again. The spin-spin coupling between magnetically equivalent nuclei also does not appear in the NMR spectrum. Okay. So that also we have seen. So then what is the difference between the magnetic equivalence and the chemical equivalence? Okay. So by magnetically equivalence means all these nuclei will resonate at the same frequency, isochronous, and they will be chemically equivalent. That also we have seen. The So this point in this point, magnetically equivalent nucleus and chemically equivalent nucleus definitions are same. But if you see that all chemically equivalent nuclei, okay, are not magnetically equivalent, then what is the difference? You will see that for two nuclei, so for two nuclei to be magnetically equivalent, they must not be chemically equivalent. Okay, that is the first criteria, that they will have to be chemically equivalent, but also be equally coupled to any other nuclei. So their coupling constant to any other nuclei have to be same. It is not only the chemical shift. Okay, it is not the chemical equivalency, but coupling constant should also be same. You can see that this, if you consider, let us say consider this molecule, fluoronitrobenzene. So you have these two hydrogens are chemically equivalent. Similarly, HB and HB are chemically equivalent. So their chemical shifts are same. These two HA will come at the same place. These two HB will come at the same place, because the molecule is having a C2 axis of symmetry and a sigma plane. Now, if you consider this, the coupling constant between this HA and HB, okay, and this HA and this HB, okay. So you see this is a 3 bond distance. Now, what is this? Will be 1, 2, 3, 4. This is 5 bond distance. Okay, so the coupling of this B, although they are chemically equivalent, 2A are different. So that's why these two HBs are chemically equivalent, but they are not magnetically equivalent. Similarly, you will see these two HA are chemically equivalent, but they are not magnetically equivalent, because if you consider the coupling of HB to HA, and this HA will be different. Okay. Okay. So, so I hope this part is very clear to you, between chemically equivalent and magnetically equivalent. So that's why you have to now distinguish. So between the chemically equivalent nuclei and magnetically equivalent nuclei. So that's why now you see in this structure, okay, you see that these two HA are chemically equivalent, these two HB are chemically equivalent, but these two HAs are not magnetically equivalent, because JAB is not equal to JAB prime for both the hydrogens. So they are chemically equivalent but magnetically non-equivalent. You see in this particular case, okay, this example, you will see that both this AB, because this is now see one, this is a 4 bond coupling, this is also a 4 bond coupling. Okay, so you see that now this JAB and JBC, okay, so sorry, both the JAB, so this and this are equal. Similarly, both these are equal. Okay, so this we will call that these both the protons are this chemically equivalent and magnetically equivalent. But similarly, exactly you see here there is a C2 axis also a sigma. Okay, so here also you will see that JAB is not equal to JAB prime. Okay, so here you will see that these two B protons and A protons are chemically equivalent, but they are not magnetically equivalent, so magnetically non-equivalent. Similarly, in simple case, if you take the difluoroethylene, you will see that cis is not equal to J trans. So they are chemically equivalent, these two hydrogens, but they are not magnetically equivalent. Similarly, these two fluorines are also chemically equivalent, but they are not magnetically equivalent, because their couplings to are different. One will be cis coupling. If you see this coupling to this is trans coupling, whereas this to this is a cis coupling, and cis and trans coupling constants are not same. Okay, so they are magnetically non-equivalent. Same thing is true for this furan molecule. Okay, so this magnetic non-equivalence also can be seen in molecules, okay, like this molecule CF3CH3, okay. Okay, so you can see that although there is a free rotation, okay, so if this free rotation, okay, because of this free rotation, this molecule can have infinite number of conformations, okay. Let us say we have fixed this conformation where this dihedral angle is 0. Now if you consider this hydrogen, okay, so the coupling of this hydrogen to this fluorine and this hydrogen to this fluorine, or this hydrogen to, or this, you can see now there are two types of coupling. So one is this, other is between these two fluorine and hydrogen, and this and this, okay. So the coupling constants are not same, okay. But if the bond connecting between these two carbon, if the rotation is very fast, then you will see that all the coupling constant gets averaged out, and you will see a average coupling constant, okay. So, but if you consider, if you fix them at a particular conformation, then you will see that all the three fluorines are also not equivalent, and all the three hydrogens are not equivalent, and then you will give them, label them as H prime, H double prime. Similarly, fluorine also F prime and F double prime. Okay, but as I told you that because of the rapid rotation, this it gets averaged out, and you get you make them magnetically equivalent on the time average, as there are three a time average for hydrogen as well as for the fluorine. Okay, but and then I told you if the rotation is slowed or stopped, you will see this magnetically non-equivalence will emerge. Okay, so now we'll tell about the Poplar spin system notation, because when you have the chemically non-equivalent proton also and magnetically non-equivalent proton also, how we express them. Okay, so what you have to do, like I have already told you that I am giving notation of A, B, X, but there are certain rules to be followed when you give this. Okay, so first thing is that you have to assign a capital letter to each magnetic nucleus involved in the coupling system, okay, or the coupled system. Okay, and then how will select the letters? Letters will be, there will be alphabetical relationship reflects the relative chemical shifts of various nuclei. That means if you say AB, that means these two nuclei chemical shifts are very close. If you put AM, the chemical shifts are in between, and if you put AX, they will be quite far away. Okay, so that is the way this alphabetical relationships reflects. Okay, so that's what I told you. The two nuclei with very different delta values or chemical shift values will be given AX, or it can be AX. Suppose there are three nuclei interacting, it will be AXY. Okay, so for two nuclei, we call this as an AX system. Two nuclei which are very similar but not identical delta values, we call them AB. And I think we have even Professor Hosur also discussed in the last class about various amino acids, and you have seen that let us say tyrosine or phenylalanine, the CH2 which is connecting to the aromatic ring, you will see those two hydrogens are not chemically equivalent, and mostly they behave as a AB system. Okay. And when we will give AM system, see this AB, AM, AX depends on, if you remember, I told you about the how it comes from the delta, the chemical shift difference, and what is the coupling constant between them. If the delta is greater than 10 times of the J value, we call them as a AX system. If it is equal to or less than delta is equal to very close to 10J, we'll call this as a AM system. And if it is delta is much less than 10J, we call that as a AB system or ABC system, depending on how many spins are there. Okay. So similarly, people, you have three nuclei with moderately different delta values. Okay. So one is A, this is the moderately different is M, and this is the another is AX. Okay. If two or more nuclei are chemically equivalent, we'll give them same letter. Okay, it can be, let us say you have a system like A3, X3 can be, let us say you have a system, there is a possibility that you can have a A3, N2, X3. Okay. Okay, so there are 3 equivalent A nuclei, 2 equivalent M nuclei, and 3 equivalent X nuclei, and their chemical shifts are different, moderately different. Okay, for this you can see that this ethyl bromide, these 3 hydrogens, we call them A3, and this CH2 we call CH2, because there is a quite wide chemical shift between these two system, because this CH2 is connected to bromine, and so automatically you will see that it comes around 1.1 ppm delta value, whereas it comes around 3.8 ppm. Okay. So now, if you see that as I was telling this example, I was telling, so we call this system as A prime, B prime, when the protons are chemically equivalent but not magnetically equivalent. Okay, so 2 weakly coupled spin system we call AX, 2 strongly coupled spin system we call AB. AB means their chemical shift will be, if the chemical shift is very close, we call them strongly coupled spins. If the chemical shift is widely different, so the coupling constant value does not tell whether it is a strongly coupled or weakly coupled. It is the chemical shift difference between the spin systems decide whether they are called strongly coupled or weakly coupled. As I told you, for three it is ABC. For if they are widely different, we call ABX, AMX. Okay, and I told you A3X3 means 3 magnetically equivalent nuclei is coupled to another 3 magnetically equivalent nuclei, whose chemical shifts are widely different, like CH3, CF3. I have already told you, under very fast carbon-carbon bond rotation. And then A prime, A double prime, X prime, X double prime, we call when CF3, CH2 under slow bond rotation. That also I have explained to you. Okay. So finally, the identical levels give spectra that are very similar in appearance. Like for example, this CH2, CH2O, if you see this fragment is present in any molecule, you will get a kind of situation called A3X2 system. Okay, so you will see a triplet due to a triplet of CH3 due to the CH2 and a quartet of CH2 due to the CH3. Okay, and you will see that JAX is equal to JXA. Okay, now you see this is a molecule. Okay, a molecule A and B. So what way these two molecules are different? You see in one case the cyclopropane ring is above the plane, and both the cyclopropane rings are above the plane, and both in the second case one is up and another is down. Okay. So automatically that changes their symmetry elements. If you see in this particular case, you will see that your molecule is having you have a C2 axis, that is your perpendicular to the molecular plane. So you will have a C2 axis here, and you will have 2 sigma planes. Okay, but here you will see there is in case of in this particular case, you see a additional, you will see the I. Okay, a center of symmetry. You can see that this point, you can see these points are, all you can connect this way. So that's why you will see that these two hydrogens in this particular case are equivalent. These two hydrogens are equivalent, but this hydrogen and these hydrogens are not equivalent. So you will see a AB system here, whereas you will see that all these hydrogens become equivalent. Okay, so you can consider that this CH2 will come as a A2 system. Okay, whereas this CH2 will come. So there are 2 AB systems here. There are 2 A2 systems here. So symmetry makes a lot of difference in the, and you will see plenty of examples in literature where although they have the same formula, only changing the stereochemistry, you see the completely, you will see the spectral appearance. I have taken another is simple molecule. It is a dichlorobutane, cyclobutane. Okay, all these ABC all are hydrogens. Okay, if you see that when for one cyclobutane, you will see that it is these two. You will see that these two B's are equivalent, chemically equivalent and magnetically equivalent. But these two B's are chemically equivalent and magnetically equivalent, but these two B's are not, they are chemically equivalent but not magnetically equivalent. Similarly, these two A's are chemically equivalent but not magnetically equivalent. So that's why the spin system will be A prime, B2 and B2 prime. Because, and you see the symmetry elements present in these molecules are C2 and 2 sigma, and you should be able to, you should try to find out whether these symmetry elements are present or not. Now you will change, now you take cis-1,2 dichlorobutane. You will see that if you do analyze on that way, you will see that none of these protons, you will see that there are three groups of protons which are chemically equivalent, A, B, and C. But you will see none of these, each group, they are not magnetically equivalent. So you will see A prime, B prime, C prime, because the coupling constant to other nuclei will be different. Okay. Similarly, if you consider the trans 1,2 dichlorocyclobutane, again you will see a very similar system. Okay, because it has and the molecule is having only a C2 axis of symmetry. Okay. Now, if you take the cis-1,3 dichlorocyclobutane, you will see that these two hydrogens are equivalent, both chemically equivalent as well as magnetically equivalent. But you will see that B and C atom, C hydrogens are not, they are chemically equivalent, both B and both C, but both the B's are not magnetically equivalent because their coupling constant to A and C are different. Similarly, for the last isomer, where it is a trans one, which contains a C2, sigma, and I. You will see that again very similar to the first one. See, first one we saw the A prime, B2 prime, because the number of symmetry elements are more here. So we will see. So what you can say that it can be concluded that compounds that have little or no symmetry will have more complex spectra than compounds that have a number of symmetry elements. Okay. Now, as I told you that although you will see that in bigger molecules, you will not see that the whole molecule there are virtually no symmetry element. Okay, still we see simple spectra. So in these cases, what you will see the groups of protons from isolated spin system. The spin system can be A2, AB, or AB2 or ABX type. That we will see it. They can be analyzed. So we will not see the whole molecule. We will rather see a group of protons. But how we'll choose this group of protons? Okay. So first thing is that we have to find out the group of protons and their symmetry. For that group of protons, you have to consider. Okay, so you need not to bother about the symmetry of the whole molecule. Okay, but under what condition? So the spin interaction between the individual proton groups lie below the experimental limit of detection. For example, this aromatic proton will not have visibly coupling constant with these protons. So we can consider this part of the molecule as a group, this part of the molecule, because this is not coupling to this side also, this side also. We can consider this as a group. You can see this portion of the molecule as a group. Okay, so you can see very clearly. So you will see that as we analyze, this is a AB2 system, this is a AB system, this is also a AB system. Okay, so that makes your spectra identification simple. So I have taken a relatively complex molecule, but if you now see that each part of the molecule is having now a symmetry. okay, which is not affected by the other part of the molecule because there is no spin-spin or coupling interaction, or the coupling interaction which is not visible. Let us see the NMR spectra of this molecule. If you see, start seeing the lines, you see that this is the proton which is coming from this isolated methyl. Okay? It is not coupled to any other, so it is coming as a singlet. Now you see that these two vinylic methyls, they are coming here. Okay, and they are not chemically equivalent because one is cis to hydrogen, another is trans to hydrogen, and there is also allelic coupling, but that coupling constant is not. That's why they are slightly little bit prudent. And these two CH2s, they are coming in the, and they are merged here, and the solvent is acetone 6, and that also comes here. So it is overlapping with that. Now you see that you have a next proton is your this CH, which is coupled to this CH2, that gives you a triplet, and then you will have the allylic coupling with this hydrogen, a very coupling constant value of, and you get a broader CHP, a triplet which is further split by the allylic coupling. Now you see that you have two AB systems. This one AB system and this one AB system. So you see this AB system will come as a just doublet, and that is coming here. You see the other proton of this. So this is your H3. So this proton is coming here, and this proton is coming over. You can see this AB system. Okay. So this is clearly, you can see the AB system. Okay. Similarly, the other AB system, which is due to this double bond, you see that it is coming here. So this is, and this. If you remember the AB, the AB quartet, or we call this is a roof effect. Okay. So you can see this AB. Okay. So that's why it is very clearly visible. Okay. Now in this molecule, you have a aromatic proton which is not coupled to anything, so that is coming here. Okay, and then you have this AB2 system. AB2 system, and you can see that this AB2 one peak is here, and merge with this, another a doublet is here. Okay, so this corresponds to 2 hydrogen, this corresponds to 1 hydrogen. Okay, and now you see that you have the several hydroxyl. So these 2 hydroxyls are coming here, and if you see in this benzene ring also there are 2 hydroxyl, but one is chelated to this carbonyl. So that chelated, I told you, hydrogen bonded carbonyl comes much downfield, which is coming here, and the lone hydroxyl, which is here, is appearing here. So in this way, even if you see the individual group of protons and their symmetry, if you analyze, a complex molecule can be, spectra can be analyzed. Okay. Now we will see the influence of chirality on the NMR spectra. Okay. We know that the enantiomers, they have the same NMR spectra. Okay. So they cannot be distinguished by NMR. Okay. But suppose if you take a chiral compound and you react with a racemic mixture. Okay. Let us say you have taken a chiral compound with configuration S and you have reacted with a racemic mixture RS. So for here, this sulfinyl chloride, so this is your chiral center. So this we have taken RS sulfinyl chloride and you are reacting this with a chiral alcohol. So you are getting 2 diastereoisomers. Now one is SS diastereoisomer, S of alcohol and S of sulfinyl chloride, and S of alcohol and R of the alcohol. Sorry, S of alcohol and R of the sulfinyl chloride. So you get, so if you record a NMR, but you will see a 2 superimposed spectra due to the 2 diastereoisomers. Okay, so you can see that in this particular case, even a 60 megahertz spectrum, you can see the 2 tertiary butyl. See, there will be slight difference in intensity because the reactivity of the 2 sulfinyl chloride to enantiomers are not same. This is called the kinetic resolution. One of them reactivity is faster compared to other. So that's why their ratio will not be exactly reflective. Okay. So more S has reacted to, let us say, S sulfinyl chloride than the R sulfinyl chloride. You can see similarly, this is one CH3 doublet, this is from another CH3 doublet. Okay, so if you have two compounds, so this CH3 will come as a doublet, you can see clearly. Unfortunately, this methyl B has come as an accidental equivalence. Okay, you will see the CH group. They are although it looks like a quintet, but they should be quartet. So you will see there is an overlap of two quartet. You can see this is one quartet, this is another quartet, and two lines are overlapping. Two lines of this quartet is overlapping with the two central lines of this quartet. So that's why it has become now a quintet, which is shown clearly here. Okay. Next class we will see how to determine the enantiomeric purity, and then subsequently to how to find out the absolute configuration by NMR. So we'll keep on telling about this effect of the effect of enantiomer in NMR spectra. Okay. Depending on how we are treating the enantiomer. We'll be putting something and there will be some change, you will see that. Okay. So now suppose if you have a molecule, that is a chiral center, as I have told you. Okay. So chiral center, so automatically if you see in this molecule, there is a chiral center. These carbon, all the substances are different. Okay. So now you have a CH2. And you will see this is true for most of the amino acids. You see that you go for phenylalanine, you go for valine methyls, you will go for leucine. You will see that one of the CH2 group that is coming very close to the chiral center. Okay, so if there is no chiral center, what you will see? You will see a A3X2 pattern. Okay, because of the oxygen is attached to CH2 is quite downfield, and automatically this X2 is nothing but the CH2 and this A3 is CH3. Okay, but now this situation is different here because it's attached to a chiral center, and you will see that these two hydrogens will no more be equivalent. Okay, so the new pattern of the spectra will be ABX3. So these two hydrogens will now be AB because their chemical shift will not be same. Okay, and you see here the CH2 group. Normal cases, if it could have been come as a quartet, but now as it is a ABX3 pattern, you get a large number of splitting. Whereas CH3 still is able to maintain the triplet structure. Okay, so now let us see a much more generalized thing. Okay, so you consider a molecule. You have the chiral center. Okay, so why these two hydrogens are not becoming chemically equivalent? Of course, if they are not chemically equivalent, they will not be magnetically equivalent. Now see, because of there is a free rotation, you can think about infinite number of conformations. Let us say there are three major conformations: 1, 2, and 3. Now, if you see this H1 in 1, okay, and H2 and 3. So this H2 is between A and B. Here also between A and B. But this H1 and H2 resonance frequencies are not same because you see the R group. R groups are in both the molecules, they are in different positions. So that's why the new 1 and new 2, 3 are not same. Similarly, you will see the new 2, 1 and new 1, 2. New 2, 1 is this, and new 1, 2. They are in the same position, but again you will see the R group in different position. Okay, so that's why in all possible conformations, even their conformation populations are different, but you will see they never become chemically or magnetically equivalent. So that's why their chemical shifts are different. See, there could be an accidental equivalence, okay, that I have told you. Even their protons are not related to each other or coupled to each other also can become chemicals, it can be same. But let us say in a particular machine you are getting a chemical equivalence. If you go to a higher machine, you will see a difference, okay. So then we will call them, they are not chemically. There is a very interesting case. See, this situation is slightly different. So you see, we have discussed earlier example when you have a chiral center. Okay. Now, let us say this is a prochiral center, like case of acetaldehyde, diethyl acetal. Okay. So you see there is a plane of symmetry. Okay. There is a plane of symmetry. Okay. But there is no any axis of symmetry. Okay, so that we know that if there is a plane of symmetry but no axis of symmetry, we call those groups diastereotopic. And that's why you see these two CH2s are now no more equivalent. Okay, and you can see that they appear rather than it's a complex NMR spectra. Okay. So that's why this is the thing, that always then if a substituent of general structure CH2R is in the neighborhood of a prochiral group or a chiral center, both in case of prochiral, the environment of X becomes non-equivalent or diastereotopic. Okay, so they come, gives you a very complex, and you can see now a complex spectrum. Okay, so you see that when see if these two groups are equal, let us say this is also CH3, then there will be a sigma plane. Then you will see that your spectra simplifies. Okay, but if sorry, if sorry, then these two, sorry, if you have a sigma, okay, you will see that these two groups are becoming equivalent. But if you consider a C2 axis, okay, C2, you will say they are not equivalent. Okay, so you see that whether there is a C2 axis or a sigma plane. That is a sigma plane, but there is no C2 axis. So that's why if you remember the definition of diastereotopicity is that there will be a sigma plane but no C2 axis. Okay. Now the thing which I would like to tell you is that when the protons are same, they are chemically equivalent. How to find it? As I told you that if they're chemically equivalent, they will not couple to each other, or their coupling constant will not be visible. Then how we will prove that? Okay. So one way to prove is that you substitute one of the carbon with a carbon 13. Okay, so if you do that, you will see that now the coupling constant of this carbon to this hydrogen and this carbon to this hydrogen will be different. Okay, so that will be like this. You can see there will be 4 lines, and once they are separated, you will see now the coupling between AM will be visible in those peaks. Okay, if you see the calculated spectra which I have shown here, this is your nu zero. So we are not taking the fully carbon 13 substituted. Even you can take the natural abundance ones also. So we call them a satellite peaks. So you will see one peak due to the CH3A. These two are from, and these two are from coming from the. So this hydrogen is A. Then this we call X, and then we call this HM. So HM is a 2 carbon separated, so that coupling constant will be, this is your this will be smaller than the 1 carbon. Okay, and now you can see as these signals are separated out, you can see clearly the coupling constant between the A and HM. And if you see record a real spectrum, now you can see these are due to the spinning side band, and the M peaks are hidden here, whereas you can see the coupling constant of A and M. Okay, this is possible because now this is happened due to because the carbon 13 has separated the chemical shifts. Okay, and you can see this. So this is one way to do this. What is the other way? The other way is to do that. You can replace one of the hydrogen, okay, with a deuterium. Okay, by deuterium hydrogen substitution. Now, if you see that if you take the 135 cycloheptatryne, which is here, you will see because of these two hydrogens are equivalent. These two hydrogens will come as a triplet, which is coming like this triplet. But if you replace one of them with a hydrogen, now you will see that these two hydrogens will make it triplet, but then there will be a coupling from the deuterium. Deuterium is not same. And you will see deuterium as spin is equal to Y. Each line will split it into 3 lines. And that the separation between these two lines is nothing but the JHD. Now you can convert the JHD into HH by multiplying that with the relative gyromagnetic ratio of proton by. So you have to use JHH is equal to gamma H by gamma deuterium and JHD. And the ratio is nothing but 6.514, about 6 times. We know that the gyromagnetic ratio of hydrogen and deuterium is around 6.5. And so indirectly one can find out it is about 13 hertz. That also seen from here also. If you see, this is about 13 hertz. If you use a carbon satellite seed, you can also find out. So the chemically equivalent protons also couple, but normally you cannot see because the chemical set is same. But you can use the alternate means to find out the coupling constant, either by using 13C satellites or deuterium substitution. So it ends there. Now let us see if there are any question. So any doubt? So next class we will go for how to find out the enantiomeric purity, and after that we will go for how to find out the absolute configuration. Okay, and then I will see the dynamic NMR spectroscopy. Okay, so you tell me whether if you have any doubt. Any doubt? So if you do not have any doubt, you can ask me in the next class also. Okay. So next class I will go for the determination of enantiomeric purity. Okay, by NMR, because that is a very useful method. Those who are doing organic chemistry, it is very useful to them. So I'll tell about that. Okay, and then absolute configuration in the next class, next to next class. Okay. So if you have any doubt, you can send emails also. Okay, so I'll stop here.
Our next class is on Wednesday.
And your next class is on Wednesday at same time 4 to 5. इसको शेयर कर दो। ठीक ছিল बस।